All right. So, welcome. So this is material selection, a good way to not break your robot. In this presentation, we're going to be talking about a brief clarification about what material science is. So, a lot of misconceptions about that within the whole world, really, the whole community. So we're going to just talk about briefly what material science actually is. We're going to then talk about common materials used in FRC. We all are building robots every year, and there are some things that we always have to use or want to use, things like that. We're going to be talking about what the best applications for most materials are, and some ways those materials tend to fail. We're also going to be talking about material selection in regards to what works, what doesn't, good selections, bad selections based on the object or what you're trying to use it for. At the end, we're going to have, hopefully, if we have time, open Q&A. But if you have any questions throughout the presentation, feel free to raise your hand, ask, feel free. This is a very open discussion type thing for me, so jump in whenever you want. So, a little about me and my qualifications to talk about this topic. I've spent about 10 years in FIRST, over 10 years if you count FLL. I've done FRC as a student in high school on 694, and I'm now a mentor for FRC 694 as well as FRC 8739. I'm also studying mechanical engineering at Columbia University, and I've taken a few too many material science courses over the past few years, but no matter how many courses I take, I still don't understand this subject properly. So, something you'll realize for those in high school right now, no matter how much you learn, there's always something else to learn, something more to figure out, and you'll find out just how little you actually know. But yeah, over my course in FRC, I've learned and witnessed a lot of different situations. I've worked with a lot of different materials. I've also experienced when those materials fail. Quite tragically, sometimes quite humorous ways, but every single time very annoying to deal with. Especially dealing with them in that 5-minute timeout that always seems a little too short, but for some reason everything decides to break right then. Yeah, those moments are not fun. Who said loud? Those moments are the worst. But yeah, so I've been mentoring now for about 5 years-ish, 4 years going on. But yeah, so I have some experience with this. So what exactly is material science? Again, a lot of people think they know what it actually is, but really when we talk about it in the common language and when we go about our day, we're really talking about material properties. So things like tensile strength, heat resistance, how much can I bend this thing until it cracks? All that's really properties of the material. Material science, by definition, is the study of properties of solid materials and how those properties are determined by a material's composition and structure. A lot of big words. In simple terms, it's talking about how a material is really formed, what is made up, like the bare bones of that material. And then, when you really get into it, you're understanding how you can change the composition of that material to make a specific property a little bit better or a little bit stronger. For example, you could understand, let's say, how, I don't know, a plastic works. But then you want to make that specific plastic a little bit stronger, a little bit more heat resistance, whatever it might be. So you're then trying to change the composition of that material, the fundamentals of it. So within material science, within like the realm of things, there are 4 main things that people study and think about changing. In this diagram, you can see that the structure, properties, performance, processing, those are all things that go into determining and understanding how a material works and how you could then change it and adapt it for your specific purposes. Some of the things that are in this diagram, it's a little self-explanatory. Processing, just understanding it, studying it, running through tests. Performance, similarly, you're testing it, checking what its limits are. What we're going to be really focusing on within this presentation are the properties of a material, because that's really what we care about in FRC. We want to know how much we could put this material through, how much it could handle, and when is it going to break. Because really, we want to make sure it doesn't break, so we don't want to reach that limit. But when people are studying material science, their main thing really is to understand how it works, then understand it enough to be able to change it, and then understand how it fails. There are many different classes of materials within the world, but these are the four main ones: metals, ceramics, polymers, and composites. Nowadays, with advances of technology, research, all of that, there are a few more additional main categories or classes that people talk about, consider, research. So those include nanomaterials, biomaterials, and energy materials. We're not going to be talking about that much today. But metals, ceramic, polymers, we're going to be going into that a little bit more in detail. But before we jump into that, composites. As you can tell by the diagram, they're a mixture. They're a mix of different materials that you're forming to make a stronger final product. Yeah. Any questions about this diagram? Pretty self-explanatory, right? Great. So, a materials tree. When I found this the other day, I thought this was really cool. For those of you, I think most of you probably took chemistry at some point. You'll recognize ferrous alloys, some of those stuff. They come up in metals within chemistry. These are examples within each category, each class, of various materials that you'll find around. These are all specific details that really are not applicable within FRC. I just think it's cool. You're understanding what you're actually using a little bit more, but for most people, understanding or knowing what a ferrous alloy is not strictly necessary. I do want to note, under polymers, I want you guys to note about thermoplastics, elastomers, those things. We're going to be talking a little bit about that later on, but those are really important. All right? So, let's start off talking about the actual stuff. No more chemistry. We're going beyond that. No more of the actual, the science stuff. We're going to talk about how we could use materials for robotics in FRC. Metals in FRC. Obviously, you're able to use whatever metal you really want. I'm going to recommend some materials are very costly, like titanium. So, listen, if you have the money to make a full titanium robot, have fun. We don't. I think most people don't have that type of money or type of machining capabilities and all that. So, we're going to talk about these. Most common FRC metals are aluminum, steel, brass, copper, iron, and there's a few others, but these are the ones that I've worked with personally and have the most experience with. First off, aluminum. Key attributes that I think are really important. They're ductile, highly malleable, meaning they're pretty easy to work with. Their main thing, they're lightweight. So they're, according to a statistic, they're a third as dense as iron or copper. So, it's a very lightweight metal, and it is fairly strong, and it's easy to work with. Compared to other metals that were listed and we'll talk about, it's a lot easier to work with, and the primary component of most FRC robots. Pure aluminum, which is considered about 99.6 or greater percentage of aluminum, is actually really soft and weak. Like it's said before, aluminum is ductile and malleable. So the higher percentage of purity of aluminum it is, the more not brittle, but the more easy it is to bend with your hands, stuff like that. I know everyone probably did it. Small like axles that are really thin, sometimes you can just bend them with your hands. Yeah, that depends on the aluminum composition, things like that. Aluminum alloys. So that's when you add other materials into and mix it in with aluminum. Generally, there are small amounts of iron and silicon to make these alloys. Aluminum alloys are a lot stronger. This is generally speaking around, it depends from alloy to alloy, but generally around like 89 to 90. That's the typical percentage of aluminum in the alloys that are commonly used in FRC. So, specifically, from what we've seen, what I've seen, the most common alloys in FRC are 7075 and 6063. Two different things. 7075 has slightly lower amount of aluminum in it, and it's mixed in and hardened with other materials so that it's a really strong alloy. It is the most common one used in FRC for things like shafts, any high like load weight or plate, stuff like that. All of that is 7075. If you look at all the robots that I pulled up here, all the metal, all of that 7075, all the shafts especially, those are 7075. We have experienced, especially this year on 694, shafts bending because they're not 7075. 6063 and 6061, they're really easy to bend. And quick tip, a lot of shafts from Rev, I believe, are actually 6063. So once you put a little bit higher or more torque on it, it's likely to bend. That costs us a lot of time and effort, and we had to spend a good like half a day to a day at the championships this past year just replacing all of our shafts because of that. So take note of that. Rev Robotics, they list it on their parts, but you want to use 7075 wherever possible. Yeah. So beyond shafts, aluminum is also used primarily for plates, tubing, all the tubing you guys use for like most drivetrains and arms, elevators, all of that's aluminum. It is the most common metal used in FRC for a good reason. Yeah. Any questions about that or about aluminum or alloys or anything like that? Cool. One thing I do want to note about aluminum specifically is thickness. So depending on the thickness of your material and how you're catting it, things like that, it makes your object a lot weaker or a lot stronger. So I have props here. This was a crossbar on our 2018 competition robot. That robot won the New York City National, went to champs, all that fun stuff. As you can see, it was bending. This crossbar held the weight of the entire robot. It's what we used to climb that year. Well, what it was attached to. Over 120 pounds of robot was going directly here, which is where the gears, where the sprockets and everything were. That's where everything ran. After a while, because of all that load, it started bending and it snapped. This cost us a match. This cost us a competition. So it is really important to understand yes, your material selection is important, but equally important is how you use that material. So something we learned after doing this is that we want to reinforce all the areas around like bearing blocks and high load, high stress areas, and make sure those are as protected as possible so that they have less load and they aren't as likely to break or crack. Also, in these images, you'll see common uses. This is the Rev Max tube. So like I was saying before, aluminum, very common. all of our tubing really is out of aluminum. So all the tubing that you buy online, yeah. What I wanted to point out here, these are from that robot, the one on the cart over there. It's our 2022 robot. This is the shooter plate and the belly pan. Both of these were machined by a water jet. It's aluminum, all that. But the reason why we wanted to use aluminum is because we wanted, for the belly plates, that year was, I think, the first time we used aluminum belly plate. We wanted to lower our center of gravity and put a little bit more weight into it. Later on, I'll show you examples of what we used to use and why we switched. But if you look over here, you'll see really thin pieces of aluminum. That's when it started breaking because we didn't leave enough clearance between the pocketing and the edges. So the plate just started breaking off when we were trying to cut it because it was so thin. So when you are cutting things or catting things, remember to think about how much open space you have, and remember that the thickness, how you're catting, the amount of space you use, all of that matters. You also want to think about the load and how much capacity it will have to carry. Generally, if it's going to be carrying like the weight of your robot or anything more, really heavy, you want it to be sturdy. You want it to be a little bit more buff. So moving on to steel. So steel is actually not a metal per se. It's not something you'll find on a periodic table or anything like that. It is an alloy of iron and carbon. Fun fact about this. You could only categorize an alloy as steel when it has a carbon concentration of up to 2%. Anything higher than 2% becomes cast iron. So you know, like your skillet, griddle, all of that, cast iron skillet, yeah, that's when it's higher than 2%. We don't want that. We don't want that on our robot, so we're going to keep it at 2% or under. So steel as a material is really durable, is really rigid, and it could be used for multiple different things. You see it all around you. You'll definitely use it every single time you build a robot. It's in your nuts, bolts, rivets, screws, all that. Generally speaking, everyone uses steel hardware just because the aluminum ones tend to bend because, as mentioned, they are a little bit more malleable. So when you're tightening something, you generally want it to be a little bit harder, stronger, and that's why you use steel. Another thing, it is heavy. For anyone who has like carried a steel plate or a bar or anything like that, you know how heavy that stuff is. It's why it is not commonly used in FIC, outside of like wanting to make your robot heavier. Yeah. Generally speaking, steel is used as ballast, so adding weight onto your robot. We could look at an example over here. Robot was a 2019 robot. 694 made. It was very front heavy, not equally balanced whatsoever. So we have to add a little bit more weight to the back. Later on, if you want to come up to speed, but there are two plates in the back over here. Both of those are about like 3 to 5 pounds of steel. So we just added that onto the back, slapped it on, just trying to even out the weight distribution a little bit more. Fun fact, if you were reading my slides on my About Me thing, I said I designed the worst drivetrain in 694's history, in recent history. That was this one. It's not a good drivetrain. We could talk about it a little bit later, but there are things that went into designing this that made it really hard to drive and just wasn't great. Anyway, moving on, steel is also used as structural supports. So sometimes within your robots, you might have something that is prone to bending or has a lot of like impact force. For example, over here, this robot had a lot of force being taken on the sides over here in front of the intake. something you might want to do is replace those angled pieces to give a little bit more support with steel. Those are not steel, but something that we did consider. Next, we're going to talk quickly about brass, copper, and iron. These are not as common in FRC, but we still see them in very specific situations. So, brass is an alloy of zinc and copper known for its hardness and workability. Generally speaking, a lot of people tend to use this as ballast as well instead of steel. It's a little bit easier to machine, but it still has a high density. So it is good material to use if you just want to add weight to your robot. Moving on, copper, extremely ductile metal, meaning it could be it's very, stretched out, it could be flexible, it's very malleable in that sense. It is also a very good conductor of electricity and heat. Remember that. Finally, iron, soft ductile metal with high tensile strength. We talked about it. It's something that's used to make steel. Common uses in FRC include, again, brass as a ballast. It's also used in fittings. So if you have pneumatic fittings, almost all of them, might be all of them, are brass. It's just a common thing. A lot of fittings within the world, fixtures like that, are brass. As for copper, think about all your wires. Every single wire you should be using should be made out of copper. It's something that is asked about during robot inspection. And I was told to mention this by a robot inspector that they are allowed to check if your wires are copper. So honestly, they'll only do that if they like really hate you or something. So, but generally speaking, all of your wires should be copper. And finally, iron. I don't like using it. I've never used it. I was told to mention it by the same robot inspector, but teams do use it as ballast again. I think that if you're going to use iron, might as well use brass or steel. Brass is easier to work with. Steel is a little bit denser. So, yeah. That's those materials, the less common ones. If you want to mention titanium, that's a thing, but I'm not going to talk about titanium. Moving on to plastics. Most common plastics in FRC include polycarbonate, nylon, plexiglass / acrylic, silicone, rubber, Delrin / acetal, various printed plastics like ABS and PLA, and urethane / polyurethane. There are obviously a lot more plastics you could be using, but these are some of the main ones that are most common. So first off, polycarbonate. Probably the single most common plastic in FRC. High impact strength, lightweight, high dimensional stability, means it could hold its shape fairly well. And common uses in FRC include, you can probably see all over here, intake plates, belly plates, electronics covers, shooter hoods, so on and so forth. People use polycarbonate for a lot of different things, but sometimes if you try to use it too much, it might not be the best situation. One thing, the most obvious one, the belly plate on this robot was 8-inch polycarbonate. We've used polycarb belly plates for a while because we wanted to save weight. This was back when we were always about 0.1 pound away from the weight limit. So every pound counted. But we face the consequences of our actions at the championships. So it's not complete anymore. Okay. So all this, the tape and all of that, yeah. So the belly plate cracked at the championships basically in half. This was after our last match, after our last qualification match, we had to get inspected, all that fun stuff. However, we have huge cracks all around our belly plate. You'll still see the cracks. We never got to replacing it. Not easy. But because of this, because it was so long, of the impact we were facing, we started wearing down time, and around the holes, all of that here. We fix that by patching it, by screwing in a piece across here to provide a little bit of support. And then we use flexing. Yeah. I'm not going to say it's my proudest moment, but it worked. So I'm not, and it's still working, like it's still here, so I'm not going to say anything about it. But after that, you're very against using Lexan belly plates simply because using 1/8" aluminum and 1/4" polycarb, similar in weight, things like that, but you could get away with pocketing aluminum and just lessening that in the weight in that regards, but it's still a lot stronger than 1/8" polycarb. Yeah. But I was saying, if you look at these robots, a lot of them have different Lexan polycard pieces, and it's a very versatile material. The picture on the left, that's the same drivetrain from the practice robot. This was a practice robot that barely got any use, and it's still beat up. So I think that shows how poorly designed it was. The one on the right, so that's the intake plate up here. But the reason why this intake plate was cracking, even though it was 4" Lexan, is because of the forces that was on it. This intake really defied a lot of the physics in some ways. It was trying to pull and push, and it was doing all sorts of things that I really shouldn't have. But because of those forces, it started cracking along the axle points. So even if you do use like a right thickness and stuff like that, where you place your forces matters. So if we'd redesign that, we would probably change how the intake is mounted and stuff like that, but we would also probably make the points around the axle mounts and crossbars a little bit stronger, a little bit wider, so that there's more material. Next, nylon, urethane, polyurethane. Please note, these are not all the same thing. They're different, but I just wanted to cover them quickly because there are similar uses. But do not make the mistake that they are similar in like composition or anything like that. So all of these are plastics, specifically polymers, that generally have high tensile strength and are flexible. That's important because of their common usage. So, nylon, belts. It is used a lot in belts. Every single belt that you use most likely is made out of nylon, which is primarily manufactured in fibers. So when you look up your belts like information and all that, it'll say nylon fibers with like polycarb or whatever. Yeah, that's how nylon is manufactured, primarily in fibers, and it is very common in all like FRC belts. Polyurethane and urethane is a lot more common in rollers. This is probably an intake a lot of people have seen this season. This is the like 111, 930, all like that intake. They use a polycord belt, which is just polyurethane or urethane, and they tie it together or melt it together to form loops that are then ran on a tube or something of their sort. This, a regular belt, it's just a nylon polycarb mix. It's a very common type of belt used in FRC, so it is a material that we all are very familiar with. Now, quick thing about Delrin and acetyl. They're the same thing. They're like different names for the same material. Delrin is sometimes like manufacturing company, but it's the same thing, really. The key attributes of this material is that they're really high in strength and they're low friction. Common uses for Delrin is in bearing blocks and plates, side plates, stuff like that require low friction. So if you look over here, this robot, all the plates down here on the side of the conveyor, all of that, that's all acetyl. We chose that simply because of the amount of friction or lack of friction it had against the balls, and we saw after a lot of testing that it just worked better than Lexan or polypoly. Also, another example of Delrin. You can't really see it in here, but on the inside of the carriage over here, those are the Delrin blocks. We machined those on the Bridgeport back there. But one thing that I do want to note about Delrin, it is really hard to machine. Maybe it's just us, but when we try machining it, it melts. It's still a plastic, so it melts really easily. And generally speaking, it was really, really difficult for us to work with and didn't provide us the results that we wanted either, especially when it came to the bearing blocks. So my advice is if you're thinking about Delrin, think of it as, or using Delrin, think of it as like for a plate or something like that. But if you want to use it for like a bearing block or applications or slide application, just use a bearing blocks that you could buy. You could buy them online. You could use actual bearings, make them yourself, but there are better options than Delrin. So quickly moving on to 3D printing plastics. 3D printing has become a lot more common within the world in general. It's probably used by nearly every team. Like you could get access to a 3D printer fairly easily. And it's a very, very powerful and useful tool. The two common ones, filaments, ABS and PLA. I like to coin it as the toxic one and the easier to print one. The toxic one, you don't want to breathe it in. You don't want to have any of those fumes around you or anything like that. That's why all ABS printers have like some type of enclosure. Or at least it's recommended to have some type of enclosure. If you don't, I'm not going to ask questions. PLA is a more common one. It's the one that's safe to use and like everyone has it. But something that I quoted from Mark Forge as of 2 hours ago because I got lazy. ABS, while weaker and less rigid than PLA, is a tougher, lighter filament more suitable for some applications beyond purely hobbyists. ABS is a bit more durable, is about 25% lighter, and has 4 times higher impact resistance. Something else that I want to note, all these materials can be then combined with other things. So a lot of people have probably heard of PCABS. It's a common material for like Markforged and Stratus and stuff like that. It's a kind of a composite that's mixing PC and ABS to make a harder, stronger material. A lot of the stuff you see on 694's robots that are printed, a lot of them are PCABS. So for this one specifically, all the black pieces, that's PCABS. We use a lot of it out here. It's expensive, so maybe be a little wary about that. Yeah. Quickly, I want to talk about wood. It is a biomaterial, so we're talking about one biomaterial today. It is very robust, depending on the wood thickness, the wood and the thickness of the wood, and it could, depending on what you use, it could be stronger than a lot of different things. It could be stronger than aluminum, probably not steel, but definitely stronger than polycarb in some applications. It really depends on what you need to use it for, but we've found, especially recently, that wood can be a really good and easy to use material for a bunch of different situations. Some common uses for wood in FRC, prototyping. If you have access to a laser cutter, it's really easy to cut, but like Baltic birchwood, that's the most common one. It's used a lot in prototyping for across the FRC community. And in fact, also bumpers, something that is usually required, except like 2015 apparently. You need to have bumpers to be able to play. There are specific requirements for it in the game manual, but you need to use plywood for it. So you have to have at least some wood around. Yeah. A few random things to add on. Generally I think that material selection is always the first step. However, the things after that, like thickness, catting, where the forces are going to be, those are equally important. So while I hope you guys learned something or like found something informative about what materials to use for what applications, but at the same time, remember that the material is just one thing, the rest of it is up to you guys. So we don't have really any time at all. But if you have any questions, feel free to come up, talk to me, ask me. If you have any questions later on, feel free to reach out to me by email. Other than that, that's the end of StuySplash. I hope you guys enjoyed. I hope you had a good day.
Sure. So what's is there a difference between resin printing and the ABS that you're talking about?
So, generally speaking, resin printers are. So you've seen like resin printers where they're coming out and
Right, it's a multi-stage,
Yeah.
right?
Yeah, and then you need to cure it and stuff like that. It's a different type of material. So ABS is additive manufacturing, where you're just going layer by layer, things like that. Whereas for resin printers, you sink the plate in, and then the laser in the printer, poking, basically firing into the filament, the resin, and then forming the shape that you want it to.
Okay.
And after it forms that shape, you take it out and put it into curing basin. That's when it really hardens and forms the final shape. Resin printers, I've worked with a little bit. I think they're really fun and cool to play with. Uh, there are a few really interesting resin filaments that that are like half rubber and half like some other material. But it really depends. I
So
think
is like resin stronger or weaker than the